Good afternoon, everybody. Welcome to the video for lesson number one. So unfortunately, I'm not going to be here for the first couple lessons of this new lesson unit on statistics. However, the first few lessons are pretty basic stuff, and I think we can get through it if we work through the video together here. So what I'm expecting you to be able to do here is take some notes along with me. Play with your calculator a little bit. You're definitely going to want to have your graphing calculator. We're not going to use Desmos for this. If you don't have a graphing calculator today or tomorrow, we'll make sure that you get one later on in the week when I'm back to school. So the first lesson, we're creating something called distributions. So anytime that we collect data, we can kind of go through and distribute the data so that we can look at whatever patterns arise. So the opening exercise asks a statistical question. What is the typical shoe size for a ninth grader at Cornwall Central High School? So one of the days last week, I went through and actually randomly asked all of you some shoe sizes, and this is the data that I got. So this is a sample of the ninth graders in Cornwall Central High School because my class, my second period Algebra 2, Algebra 1 class, is a sample of all ninth graders. I have some students in that class that are athletes, some boys, some girls, some students that are non-athletes. So it's kind of a good sample of everybody in ninth grade. So if we take a look and we kind of go through here and plot all of our data, we can reveal if there's any type of pattern that arises. So all I'm going to do is I'm going to take each shoe size and make a dot above where that number would be on my little number line down here. So my first dot would be at 9.5. My second dot would be at 8, at 12, at 9.5 again, at 7, at 10.5, at 6.5, at 7 again, etc. And you should do this along with me so that you can make your dot plot as well. And that should represent all of our shoe sizes in the class. So looking at this, it asks us what is the range of our data. So looking at our list, if we organize it in this dot plot, we can clearly see that the minimum data is at 6.5. That would be the smallest shoe size in class. And the maximum data point was at 13. So the range of our data is from 6.5 to 13. It then asks us how many people have a shoe size that is 8 or larger. So looking at our data here, I'll use a different color actually. If I take a look at the box that would be representative of all of the data points that are at 8 or above, all I'm doing here is counting them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 17 people with a shoe size of 8 or larger. So one of the things that I'm hoping you're noticing about this dot plot that we've created, it's just a nice way of organizing your data. Instead of it being just all randomly mixed by just asking people, right? It would be hard to determine from that original little setup that we had there what the largest value was, smallest value was, or just in general how many were more than or less than a certain value. So the dot plot is a nice way of obtaining a nice organized way of our sample data. Another way of creating or organizing our data is in a form of a histogram. So in 2006 and 2007, Arlington High School varsity boys basketball team had an excellent season, compiling a record of 15 wins and 5 losses. The total points scored by the team for each of the 20 games listed below. So what we want to do is we want to organize this data in a way where we know how many of the games they scored in different ranges of scores. So looking at this, if we go through and tally each number, so 76 would fit here, 55 would fit here, 76 would fit here, 64 would fit here, etc. And you could go through and finish this tally on your own. You might even want to pause the video for a second and try it, and then see if you got the right answer. Notice how I'm crossing out each one as I make my tally so that I don't double count one. So then the frequency is how many of each of those scores that they had. So they had 3 scores between 40 and 49. They had 1, 2, 3, 4, 5, 6, 7, 8 scores between 50 and 59. 1, 2, 3, 4, 5, 6 scores between 60 and 69. 2 between 70 and 79. None in the 80s, and 1 in the 90s. They had one really good game where they scored over 90 points. Look at that. So if we want to create a histogram, hold on one second. Okay, so if I am creating the histogram here, I need to create a vertical axis that represents our frequencies. So here's our frequencies. The highest frequency I have is 8, so I know I have to at least go up to 8. So go 1, 2, 3, 4, 5, 6, 7, 8. And horizontally, I want to make bars for each of my points scored, including the one that has a 0, right? We want to show that. So I have 1, 2, 3, 4, 5, 6 ranges of numbers. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have more than 12 boxes, so I can make every 2 boxes a range. So this would be 40 to 49. This would be 50 to 59. This would be 60 to 69, 70 to 79, 80 to 89, and 90 to 99. I don't even need that last one. And then all I'm going to do is I'm going to make a bar that shows the frequency for each range. So I have a bar here, color it in. 50 to 69, I'm going to go all the way up to 8. I'm going to make a nice bar, color it in. Go up to 6, make my bar, color it in. Go up to 2, make the bar, color it in. Don't have a bar for 80 to 89 to show 0. And this last one is the smallest one where there's just 1. So some advantages to using a dot plot. So if you look at the last example, there weren't many of you that had the same exact shoe size. So we were kind of random when it came to shoe size, right? So some advantages to using a dot plot is when not many values are repeated. Advantages to using a histogram is when we have like a range of data or we have repeated values. So if I have a lot of values that are the same number over and over and over again, instead of making a million dots, I could just make a bar to represent how many of those dots are represented there. So whenever we're talking about like ranges, usually we use a histogram. When we're talking about single types of pieces of data, we usually use a dot plot. All right, so now we've created a histogram. The last thing we have to do for all of our histograms is we have to give it a title, right? The title is going to be something that we want to put on every histogram that we have here. So we've labeled our frequency, we put our scores, and on top we'll put Arlington basketball scores, something like that, okay? Number three says that we have a histogram of test scores. A student is considered mastery if they have obtained an 85 or higher. How many students have achieved mastery? So if you look, you're only looking at the bars here that I'm going to shade in purple. Those are the only bars that are above 85. So there are 25 here. There is, looks like to be 16 here. And 1, 2, 3 over 95. So all I'm doing is I'm going to add those three numbers together. Use my trusty calculator there. 25 plus 16 plus 3 gives us 44 students. So we're just reading the bar graph here. We're reading the histogram. So the next question says, can we determine the range of the distribution? The lowest score to the highest score? And for that question, we can't, right? So we can't because we don't know the lowest or highest score. So one negative part of histograms is, yeah, we're organizing the data, but I don't know what the actual scores are here. I just know that these three scores are between 95 and 100. I don't know what their actual score is. They might have gotten a 97, a 98, a 99, or even 100. I don't know. I just know that there are three scores within that range of data. So that's one negative to histograms, which is why a lot of times we use dot plots. The last question here says 22 students scored from 80 to 84 on this test. Does the histogram provide us enough information to conclude that a student must have scored on 82 on this test? Explain your reasoning. So because there are 22 scores between 80 and 84, I'm going to assume at least one of them is an 82, but I don't know for sure, right? So we don't know for sure if any kid got an 82 exactly. I do know that there are 22 kids that scored between 80 and 84. All right, I could have had all 22 kids score an 81, and that would have filled that bar. I don't know for sure if anybody got an 82. I just know that there's 22 kids between those two scores. All right, so let's talk about the shapes of our distribution. So there are three main shapes that we try and have our distributions come out to be. One of them is our favorite, and we'll talk a little bit more about that, especially once we get to Algebra 2. So there are three shapes being shown here in our histogram. The first one is we call a normal curve. This is symmetrical, where we have approximately the same number of data above and below the highest peak, which is in the middle. This is a constant. Notice all of the bars are about the same height. Doesn't have to be perfect, but it's approximately constant or consistent. If we look at this next one, we see that the highest peaks are over here to the left, and most of our data is below the middle. So we call this skewed right. Where these higher numbers here, like this piece of data, is skewing all of the averages to the middle. The last one, if we look at this as a curve, right, most of our data is over here to the right, so this low number is going to skew the average to the middle. So we would say this is skewed left. So if you think about it, if Mr. Hines gave a test, which one of the test scores would he want, right? Like if it was skewed right, that would mean a lot of the kids failed and only one or two kids got a 100. If it was skewed left, that means that the test was really easy and a lot of kids scored really high on it, but one or two kids really did bad on it. A normal curve means that a lot of kids did well on it, some kids did poorly on it, but the most of the kids got an average score. So we'd actually want a normal curve because it's a balanced score, right? That would mean I created, or Mr. Hines created, a fair test where a lot of his kids did well, some of his kids did, not so great, but the majority of the kids did right in the middle, right? So a lot of kids got in the 70s and 80s. All right, let's take a look at number 4. Number 4 gives us this dot distribution of Charlie's Food Factory and their employees' ages shown in the dot plot. It says describe the shape of the distribution. So looking at the distribution, the majority of the people are really young and there's only a few people that are really old. So the really old people are going to skew the overall average of the ages of the people that work there to the right. So this is considered a skewed right distribution. The range of the data. The youngest person that's working at this factory is 16 years old. There are 2 of them. The oldest person working at this factory is 42 years old, and there's 1 of them. So the range of this data is between 16 and 42. And then it says, would you describe the age of a typical worker as 20 years old or 24 years old? So a typical worker here, if you look at the 2 bars that are, or 2 dots that represent 20-year-olds and 24-year-olds, there are more 20-year-olds that work here. 20-year-olds is the highest number of dots. So it would be more typical to be 20 years old than 24 years old. And at this point, you should pause the video and try the homework assignment for lesson 1. If you still have time in class, you can then unpause the video and check your answers to the homework, which I'm going to go through here in the next minute or so. If you don't have time in class to go through the homework and check the homework answers, you can do that at home. But the homework assignment is part of this as well. So go ahead, pause the video, try these questions yourself. All right, so I'm hoping that you paused the video and you've already tried these yourself. So I'm going to go through these a little bit quicker than I did the notes. So for the first question, we're talking about a farm and chickens, and it gives us a list of all the chickens' growths. And we want to put their weights in this dot plot. So I'm going to go ahead and make our dot plot. So I have a dot for 2, 1, 3, 4, 2 2s, another 3, another 1, 5, 3, 2 4s, 5, 6, 2 3s, another 5, another 4, 6, and one last 3. There's your dot plot. So if I was to describe the shape of this distribution, it looks like it's a curve that where the highest peaks are in the middle, There's some data below, there's some data above those highest peaks, so we're going to say this is approximately a normal curve. The range of this data is from 1 to 6. Is the typical weight of a chicken closer to 3.5 or 5.5? So 3.5 would be about here. That would be where some of the higher peaks are. 5.5 would be here. So what would be more typical? So 3.5 would be in this range here. So that would be closer to the average of all the chickens, which we'll get to in another lesson. But for right now, I just want you to notice that the number 3.5 is where more of the dots are compared to 5.5. Number 2 says, consider a histogram of Team Arb's obstacle course. So here's the team, it's a histogram. How many people are on Team R? So we have to find the total number of people. So we have 3 people, we have 8 people, we have 6 people, 2 people, and 1 person. So if we add those numbers up, we get 11, 17, 19, 20 people are on the team. If we were to describe the shape of the distribution, it looks like we have higher stuff over here and some outliers to the right. So this would be a skewed right graph. Can we determine the range of the distribution? Not really, right? We can't determine the range because I don't know exactly what the lowest number is, right? So the course times are in ranges from 4 to 5 and from 8 to 9. So I don't know if the lowest number is 4, if the lowest number is 4.5. I don't know if the highest number is 9 or 8.5. So we can't. And the reason why is because the data is shown in a histogram versus a dot plot. What would you define as a typical time for a member on the course? All right, so the highest histogram bar is at 8, and that's between 5 and 6 seconds. So we can say between 5 and 6 seconds on the course. On the next page of the homework, I gave you a dot plot. This talks about viewers of a television show. It's kind of organized in a way where we have some really low numbers, but we have lots of dots to the right. So if we show this as a little curve, we can see the highest part of the curve is way over here to the right, meaning all of these data points to the left are going to skew the overall average of age. So this is going to be a skewed left curve. Do you think the typical viewer age is 20 or 60 years old? So if you look at where 20 is here, 60 is here, right? 60 has more dots around it than 20 does. So we'd say it's more typical for a 60-year-old person to be viewing this television show. Just because there's more dots around 60, there's less dots around 20. Because this is a dot plot, we can actually find the range of this sample. So this person here is, these are going up by 2s, 2, 4, 6 years old. These 2 people here are 72, 4, 76 years old. So the range is from 6 to 76 years old. Why might a histogram be better to display this data? Right, so we can show age ranges instead of having everybody's individual age. So we can say like the range of viewers that are between 0 and 10, 10 and 20, 30 and 40, etc. The last question is kind of a think question. If you were an advertisement company, what would you want to study about the results of this data? Well, it looks like whatever this TV show is, more old people watch it than young people, right? So we would say older people are more likely to watch this show. So if you're an advertisement company and you're advertising for this show, you want to advertise it to the older viewers because they're more likely to watch the show. Hopefully this lesson made sense and you were able to decipher through it with the video. If you have to go back and rewatch the video to understand it better, you can. And then next time I'm in class, you can ask me some questions on it. See you soon.